Hello, my name is Feng Long. I am an SMA postdoc fellow at the CFA. Today I'm going to talk to you about our recent work on the comparison of dust emission in ring disks based on ALMA observations from two wavelengths. As we all know that the first detection of such dust rings is found in atrial tau, which have then inspired most of the following high-resolution observations with ALMA in disks. So our ALMA survey in Taurus is one of the many examples. We have observed the 32 disks selected in Taurus at 1.3 millimeter with 0.1 arcsec resolution. So we are able to map the dust emission variations on 10 to 20 AU scales. We found that about 1/3 of our sample show such dust substructures, mostly seen as concentric gaps and rings. Those substructures emerge from disks with both bright and faint millimeter emission, and their central stars spans the full range of spectral type covered in our sample, from early A-type stars to M3 stars. Well, besides those interesting features detected, in the remaining 2/3 of our sample, dust emission is mostly confined in a more compact region. Those systems, however, share similar distributions in terms of disk brightness and stellar mass as compared to their counterparts with detected substructures. So if you are interested in a general comparison and discussions among the full sample, I would recommend you to take a look at our papers as listed here. In this talk, I will mainly focus on 3 disks in which substructures are indeed detected. So we have conducted follow-up observations at ALMA band 3 for those 3 disks with comparable resolution of 0.1 arcsec. The selection of the 3 disks is mainly guided by their different numbers of rings detected. In the meantime, the 3 disks have very different stellar type and also millimeter brightness. The comparison of the images at 2 wavelengths clearly shows that dust emission is very similar for all 3 disks at both wavelengths, although the emission at the longer wavelengths is detected with a bit lower signal-to-noise ratio. So to guide our comparison, we have first extract the azimuth average radial profile as shown in the color lines here. Also, we have overplot as gray lines the measured peak ring location as identified from UV plane fitting based on the 1.3 millimeter data. So we can clearly see that the same dust ring is always detected at the longer wavelengths. While in the first ring of geo tau and the dust ring around ds tau, we find a relatively higher gap ring contrast. Those 2 rings are marginally resolved, while in the 3 rings of geo tau, they are mostly overlapping and largely unresolved. So with measurement of dust emission at 2 wavelengths, we can easily construct the spectral index profile as shown here in the lower panels. There are 2 main features associated with those profiles. First, we see a gradual increase of alpha value when moving to larger radius. In the inner disk, alpha value is close to 2, which means that dust emission in the innermost region is likely optically thick. While moving outwards, we see local variations of the spectral index, especially across the gaps and rings. And specifically around the ds tau ring and the first ring of geo tau, we see that the spectral index reached local minima around the peak location of the dust ring. Such features have been observed also in previous multi-wavelength observations. Well, in order to interpret the green property from those spectral indexes, we have to make assumptions about the emission to be optically thin. Such assumption is likely valid in our cases. So here now we are showing in the upper panel, the optical depth profile in our disks. The dust temperature is taken as the midpoint temperature calculated simply assuming a irradiated flaring disk structure. So the temperature scales with the stellar luminosity. We found that in the outer disk where our dust rings reside, the optical depth is at most 0.3 to 0.4. So given such low optical depth, we can construct the green opacity index profile based on the spectral index profile. In general, a lower opacity index beta will indicate the presence of larger grains. So in that case, we found there might be enhanced grain growth and the presence of larger grains in the inner disk and also around the ring location. Well, even though we found those variations of opacity indices, the inference of the exact green property based on the indices would be more complicated. For example, we have to take into account the scattering property of dust grains. Well, this is still not well quite understood. In the meantime, the absolute indices value can also vary with uncertainty induced by the resolution observations. For example, if the rings are not fully resolved, we would likely overestimate the indices in the ring and underestimate it in the gap. That being said, high resolution observations to fully resolve the gap would be highly appreciated to better constrain the opacity indices. Towards a global view, we found that the emission is quite similar at both wavelengths, which will point to a very similar dust disk sizes if we're adopting the widely used definition in the literature as the fractional flux radiuses. Given the fact that dust emission at different wavelengths tracing grains of different sizes, these consistent green dust disk sizes can be understood in terms of dust evolution models. So in the right panel, we are showing the dust disk size evolution with time for grains with different populations. In the case of a smooth disk, where the pressure is high in the inner disk, we found that after 1 million year evolution, the two populations of grains will have very distinct disk sizes. This is because larger grains will have larger inward drift velocity, and so they will be more quickly depleted in the outer disk. Well, with the presence of pressure bump in the disk, large grains of all sizes will accumulate locally around the pressure maxima instead of drifting inward towards the inner disk, in such a way that the outermost pressure bump will roughly set the outer disk radius. So our observed features of similar morphology and similar radius can be explained as the presence of pressure bump. Alternatively, the presence of pressure bump could be directly tested with observations. The dust evolution models also predict that larger grains will be more affected by the local pressure gradient, so they will form an even narrow distribution. Therefore, by comparing the ring weights at different wavelengths, which tracing grains of different sizes, we could test this scenario directly. In our best case of ds tau, however, we found that the dust ring weights are mostly comparable at the two wavelengths, or we see a slightly weak hint for a smaller ring at longer wavelengths. This result is not unexpected, given the fact that the ring weight difference predicted by models is very small, which is much smaller than our observation abilities. So there's ways, of course, ways to work around, right? We can go for higher resolutions to fully resolve the disk and directly tell the difference of ring weights. Alternatively, we can move to longer wavelengths where the ring weight difference will be larger, that will be more easily detected. Such observations might be routine if NGVOA will be on board soon. So to conclude, we have observed 3 disks at both wavelengths with ALMA. We found that those 3 disks show very similar dust emission morphology, and such pattern can be explained as dust trapping in the pressure bump. Also, we found that the low opacity indices in the dust rings suggest the presence of larger grains. Combined with high density dust rings, we think those regions might be the more promising site for young planet formation. Of course, we would highly appreciate high resolution observations like AU scale resolution to fully resolve the disk and to help us to draw definitive conclusion on the origin of such features and their associated green properties. With this, thank you for your attention.